Good morning. My name is Brantley Fry. I'm Senator Doug Jones' State Director, and I'm so appreciative that you all are here this morning and want to thank UAB and all of the team here that helped put this together with Senator Jones' office. This morning it's my distinct honor and pleasure and really just a lot of fun to be able to introduce Dr. Matt Might. Matt moved to Birmingham a couple of years ago with his family, and before I took this job, I worked for a company called Chalker Group, and I was on the team that helped recruit Matt and Christina, Bertrand, Victoria, and Winston to Birmingham, and we are so thrilled that they're here, not only because they're great personal people, but also because of the groundbreaking work that Dr. Might is doing here at UAB and as the director of the Hugh Precision Medicine Institute. Matt has a remarkable story in how he arrived in this place. He has a background in computer science, and when Bertrand was born, it became clear that something was going on that just wasn't right. And so Matt started doing research through his computer science background, was able to identify the genetic disorder that Bertrand has, and was really the first patient with NGLE1 diagnosis, and Matt has gone on to find additional patients, and Christina, his wife, is the executive director of their foundation with the goal to find a cure for NGLE1. Before coming to UAB, Dr. Might was the director of the Precision Medicine Initiative under President Obama, and Matt also served as a strategist in the current administration before coming to Birmingham with UAB. He also served as an informatics faculty member at Harvard University Medical School. So without further ado, I'd like to introduce Dr. Matt Might. Thank you all.
Yes, well, thanks. It's certainly a pleasure to be here, and I just want to get out some thanks right at the front. So first of all, I want to thank the Bidens for the energy and the enthusiasm that they have put into cancer, starting with the moonshot back when I was serving in the administration, in which I had the pleasure of working on at times there. And then, of course, Senator Jones for galvanizing this and bringing this summit to Birmingham, and the School of Nursing for providing this wonderful space to actually to give this lecture. So, you know, my goal for today is really to present a battle plan for the war on cancer. What I want you to do is to understand why cancer is such a difficult disease and why the war on cancer has been so hard. But also, again, to leave you with a sense of hope that this is a war that ultimately we can win, and that I'm impressed with the strategies being taken by the Biden Cancer Initiative and actually going after this. So let's start off at the very beginning with the war on cancer. And I think, when we declared the war on cancer way back when, I think we made a fundamental mistake. And I think the mistake was that there's no such thing as cancer. It should have been, right from the start, the war on cancers. And let me clarify what I mean by that. I'm not just talking about breast versus lung versus colon. It's actually, the problem is cancer is not one disease. Cancer is, in fact, many diseases. In fact, it's many rare diseases because, in some sense, every cancer manifests differently in every patient. In fact, it's even more complicated than that because if you look inside every patient, every cancer is different even within that same patient. That is to say, even within one patient, that patient doesn't get cancer, they actually get multiple cancers. If you just look at what's the structure of the cancer underneath. And we're going to get into a little bit of technical detail, not too technical, I promise, just so you understand what I'm talking about. But this is something you really need to understand if you want to understand what we're doing in precision medicine and how we're thinking about treating cancer from our perspective. So each of those cancers inside a patient really is its own rare disease. And then this is going to become important. And so when I approach cancer, I approach it from the background of somebody that's been thinking about rare disease. So if we want to beat cancer, what do we have to do? If that's really what it is, if it's really multiple rare diseases per patient, then ultimately we have to beat rare disease. In some sense, these battles are one and the same. And I think it's hard to imagine beating cancer without also beating rare disease and vice versa. So how do we beat rare disease? Well, that's where precision medicine comes into play. So what is precision medicine? Well, I'll go back to my old boss when he launched the Precision Medicine Initiative and used his definition for it. So he said that precision medicine is data-driven medicine. And so if you're using data to optimize the healthcare of a patient or of a population, you are doing precision medicine. Now, there's a piece of data that everyone's very excited about, not surprisingly, that's the genome. So this can be the human genome, or it can be cancer genomes, which obviously is very related. And this data has given us unparalleled resolution on the root cause of disease, both for rare diseases and for cancer. And it's really changing the game in many ways. So we'll talk quite a bit about that. But ultimately, what we're trying to do with precision medicine, whether it's a rare disease, whether it's cancer, Alzheimer's, depression, you name it, is to always find the right drug for the right patient at the right time. And again, now that we have all this data and this molecular resolution on disease, we can actually think about doing that. So, in a nutshell, if you want to visualize this, we take a patient, we extract from them their data, in this case their genome. We identify the mutations or the problems with that data that are causing their disease, and then we use that information about that root cause to find the best possible medication for them. So that's really what we're doing. And I do think of this as a process, and we're going to talk a little bit about what that process looks like. And so the question is, how do we do this process over and over and over again for every patient that walks in the door? So first, now I'm not going to go too deep here, just a little bit of biology so we're all on the same page. So DNA, let's think of it as a cookbook. We're gonna go from this analogy into what cancer is. Now it's a funny cookbook because there's only 4 letters in the alphabet that you write it with. It's A, T, C, and G. So these are the nucleotides that actually make up DNA, and so you get these strands of it. And what you really have here is a set of recipes in this cookbook. And in this cookbook, essentially you can think of a gene as a recipe. It's baking a protein. For the most part, but it really is a recipe for building a protein. So it's kind of like a cookbook and the operation manual for the human body. All right. So if you get a mutation, you change some letters in the cookbook, you might change the recipe. Maybe you get a substitution. Maybe it's this butter for this oil. Now, if it's a butter for an oil, maybe that doesn't change the recipe so much, so sometimes mutations are harmless, but not always. Sometimes a mutation actually does something bad. So some are harmful, and certainly in the case of cancer, they are as well. So the reason it's useful to think about rare diseases is that they're sort of the simplest case of precision medicine, because with rare diseases, what you have is typically just mutations in one gene. So when you're fighting a rare disease, you're really focused on just one gene at a time, and in many cases, even just one mutation. So it's about as simple as it gets for precision medicine. So just to highlight what I mean by this, and then to tie this into cancer, I want to talk about my favorite model organism, which is the stick figure. The reason I like stick figures is that they only have 6 genes, A, B, C, D, E, and F. So let's imagine this stick figure gets a genetic disorder. So now, and let's say that this stick figure got a mutation in gene C. So something happens to gene C, it's malfunctioning, and this has an effect on the stick figure. So in this case, it shrinks their head. All right. So how do we help the stick figure? Well, we got to go back, look at that root cause. In this case, it's the loss of gene C, and we have to compensate for that. We have to somehow bring C back up or find a way to account for the fact that C is misbehaving. Now, if we can do that, if we can find a drug that acts on gene C, well then, hopefully if we give it to the stick figure, their head grows back. That's the hope. That's the precision medicine for stick figures in a nutshell. Now, human beings are a little more complicated because we have 20,000 genes. It's not quite as easy with stick figures. But it also allows me to talk about why cancer is an extension of this problem. So cancer is you're rarely fighting just one gene. In cancer, many genes actually start to mutate, and that makes it a much bigger challenge. So for example, if you have stick figure cancer, then 3 genes could be out of whack, and so suddenly you have to find drugs to act on 3 genes. But it's worse than that because, as I'll explain in just a second, cancer is adapting. It's always staying one step ahead of you, and so you find something that works for those 3, and then maybe it adapts, and now you have to go after a new target. So cancer is just hard. But it's in a line that extends from rare disease in terms of how we think about treating it. So how does cancer really work? Well, you've got a human being, and for now, let's just look at a human being as a giant collection of cells. So these are all the cells in that person. Let's focus on a single cell and look at how cancer develops. So you've got some DNA inside the cell. At some point, a mutation happens. So something goes wrong. One of those letters changes. Now, normally what happens, this actually happens a fair amount, you've got little protective mechanisms inside the genome. So one of these little protective mechanisms comes out, it sees that there's a mutation, and it takes an action that prevents this mutation from becoming a problem. Sometimes it can repair it, sometimes it just destroys the cell, but in any case, that mutation is no longer a problem. Well, what happens, however, if the mutation takes out the protective mechanism? This is usually sort of the first step in what goes on with cancer. So you sort of lose the ability to protect yourself from mutations in some cell, and then all of a sudden, mutations start popping up all over. But now there's no firefighter to put these fires out, so there's sort of a cascade of mutations to deal with. All right, so at some point, one of these mutations is going to land in a gene that triggers growth. These cells are going to start dividing, so they divide, they divide, they divide, they divide. And so that, and again, at a very high level, is sort of what we're dealing with cancer. It's a cascade of mutations that ultimately causes this original cell to sort of grow without bound. And so again, that's why there's multiple mutations that we're dealing with, and what we're dealing with is now sort of a life form inside of us that started as us, but is now undergoing evolution as it grows. So that's the other thing to mention, is that tumors evolve, and this is why it's such a difficult disease to treat. So let's suppose you start off with the one cell that is we'll call it yellow cancer for now. Now, as it divides, again, it continues to mutate. So as it divides, you might end up with red cancer, and then also blue cancer. So if you treat this, you might have a drug that works on yellow and red cancer, but not on blue. So you apply the treatment, a lot of the cancer disappears, but the blue stuff stays behind. It might even be just a few cells that stay behind. The problem is they regrow. And these blue cells, as they regrow, they know how to beat the drug for yellow and red. So you try the same drug, but this time there's no effect. The cancer is resistant to the treatment you tried before. And this is what I mean by cancer is evolving inside of you. And that's why there's not just one cancer, there's many cancers inside of a cancer patient. So this is why it's so hard. But this is really what's happening with cancer today. So that's why you're always having to find a new treatment when the cancer comes back. So in some sense, cancer is like curing multiple rare diseases on the fly. So cancer is hard in that sense. So it's hard enough curing one rare disease, but cancer is like curing multiple, but you're also under heavy time pressure because this thing's going to keep changing as you apply treatments. So to some sense, if we really want to cure cancer, we really have to figure out how to cure all rare diseases. But how do you cure all rare diseases? This is a major challenge. And what I'm saying is we need an algorithm. Process for going from a patient and their data into a treatment for them. So in more lay terms, what we really need is a battle plan, a plan of action that says if this is the gene, this is where you go next in terms of finding the treatment. We have to find ways of systematically attacking the mutations that pop up. It's the same problem for cancer or for rare disease. So I'm going to show you the algorithm in very high speed. We're not going to go into any details for that, but it really starts off with looking at the genetic cause of the disease in that particular patient, finding mutations that could be drivers, figuring out which one it is, and then once you find the mutation that's driving the cancer, you look at what exactly it's doing to the patient, and from that you have a whole bunch of decisions that come after that, and you decide, okay, well, if it's this is the treatment approach we're going to take to finding drugs. If it's that, you're going to take this other approach to finding drugs. But the point is, we've mapped out a strategy that takes mutation and takes you down a series of steps to find a drug for that mutation, to counter the effects of that mutation. This is something we actually do at the Institute. So the question is, will it work? Can you actually do this in practice? And the answer is yes. It actually has worked, and it will continue to work better and better. So I'll just briefly share a summarized version of my personal story, which Brantley alluded to, and how I got into this process in the first place, and how I started conceiving of this battle plan for rare mutations and for cancer. This is my son Bertrand. He's 10 years old now. He's a happy 5th grader at Mountain Brook Elementary. But this is way back when he was about a year old. And when he was born, we had no idea what was going on with him. He was having seizures, he had developmental delay, he had a lack of tears, like he could cry, but he wouldn't make tears, and he had a movement disorder. So this was our life for, 4 years. For 48 months, we had no idea what this disease was, until finally we were able to partner with a team of scientists at Duke University at the time to do what was called exome sequencing, to look into Bertrand's genome to try to figure out what is the mutation that is causing this disease. And what they came back with was actually pretty astonishing. When we looked at the data, we found that there's mutations in this gene called NGLY1, and it looked like he was the very first patient to ever have this disease. So we were pretty sure that this was driving his disease and that he was actually the first known patient to have this disorder. So I said he's the first one we've ever seen. He's the only one we know of, so he really is an N of 1. And at that point, they also said, and there's nothing you can do. There's no drugs you can take, no drug company will ever care about this, and we can't even give you a prognosis because no one's ever seen this disease before, so we don't know what it will do. We don't know how long he will live. But yeah, I think, as a scientist, and I think I speak on behalf of all scientists when I say this, there's always something you can do. If you're a scientist, you can do science. You can just keep going. So that's really where we headed. So I'm going to skip over large fractions of this. So if you want to know about sort of the first several years of what happened after that, there's a wonderful article in the New Yorker you can read. So let's just skip ahead to finding a treatment. I think this is the part that's really relevant to today. So how do you find a treatment for essentially the rarest disease in the world? Well, the thing is, even though it was a rare disease, we finally had enough data. So if you collected all the data from Bertrand from his records, if you take these data points and map them onto this underlying genetic cause, we knew a lot about what was happening with Bertrand. We could see exactly what we needed to do, or at least, in theory, what we needed to do. We could understand what this gene was and what happened in its absence. So the gene, I won't go into, again, too much detail. The short version is it's a recycling enzyme. So if you take out a recycling enzyme, trash piles up. That's the short version. So when you look inside Bertrand cells, there's a particular kind of cellular waste that is accumulating. That is the cause of this disease. And in fact, after a couple years of studying this, pushing the science of this disease, we could see that there was a particular way that it was accumulating. And we can make a prediction at that point about what might actually be a treatment for it. And this is a process that we go through every time when a rare disease case walks into the Institute. It's the same thing we go through with cancer cases too, and we're looking at the mutations driving them. We're thinking, how do we find a drug that counteracts the effect of this particular mutation? And we get into this very deep biological reasoning. In this case, I could predict that the things that were building up in his cells were actually blocking something that he needed. I could predict that he was actually deficient in a compound represented here by this little blue square. The amazing thing about this is that actually if you Google what this is, it's called N-acetylglucosamine. You can buy it on Amazon. So I did that, and I took a bottle of it myself to make sure it was safe. I didn't die, so I assumed at that point it had passed, at least for my household, FDA phase 1 safety testing. And then I gave it to him. And the remarkable thing is, with Bertrand, after about 3 days on this compound, he actually cried his very first tear. So I did what any parent would do at that point. I collected this tear, I packed it onto ice, and I shipped it to a lab in California for analysis. Because that's what you do when you're a crazy rare disease parent. But this was the beginning of an odyssey for us. So it was one small tear for Bertrand, and he's cried many more since, thanks to this compound. But it really became an ocean of science for the disorder as a whole. And I'll just add, because I have to always add this, that when I speak to a room like this, you're like, that's great. But if I give this talk to biologists, what they say is, well, that's great, but we're biologists, and it's wonderful that it works on people. What we want to know is, does it work on flies? So we've actually built a fly version of the disease, and sure enough, it does work. So it has about a 17% survival rate if you're a fly with this disease. But on this compound that we give to Bertrand now, they have about an 80% survival rate. So strong evidence that this is a very good thing for Bertrand and the other patients. And then I just kept going. I'm going to skip a lot of details, but I found myself trying to find ways to tie biology and medicine into computer science, and this is in many ways the essence of precision medicine, to leverage the full power of computation and data to see what we can do. So I actually did computational simulations on a drug target for this disease, and after checking to see if there was 200,000 different small molecules that would interact with this structure and with this disease, we actually found 70 that did, all on a computer. And then we took 14 of those to the lab and actually checked to see, we took 14 which were FDA approved to the lab and checked to see if any of these would actually work for him. And sure enough, one actually did. So then that one that worked was Prevacid. So Prevacid and this other compound, N-acetylglucosamine, are very effective treatment for his disease now. He's been on both of these now for several years, and it's made a very big difference for him. And this mimics a similar process we might be going through someday for every single cancer patient and for every single rare disease patient. It might actually take that much, it might actually be that intense. So the question is, can you repeat this? Can we really keep doing this over and over for every rare disease patient and for every cancer patient too? And being able to give you a partial answer to this question, I'll just say that I got very lucky. I had an extraordinary sequence of opportunities Starting with an invitation to become a professor at the Harvard Medical School, which of course I had to say yes to, despite the fact that I have no medical qualifications whatsoever. And then I got called to the White House, and he said, President Obama said, I'm impressed with what you've done with your son, and I want you to help us launch this initiative to do this for all Americans. And I said, okay, I will help, whatever you want. So I started working on the Precision Medicine Initiative, and while doing this, I also co-founded a company dedicated to doing this specifically again and again and again for genetic epilepsies, just because I thought this is something that's real that we can do now, that can help a lot of people. I did actually spend some time, working on the Cancer Moonshot on sort of the informatics side of that, so that we would be able to collect the right amount, collect the right data, and manage it appropriately. I did a lot of work for a large cohort program called the All of Us program, which actually you can enroll at here at UAB. I helped bring precision medicine to veterans through the Million Veterans program. And, but really, through all of that, the mission was clear. It was, let's do this again. Let's repeat what we've done for Bertram, but do it for other patients. And by the time I'd arrived at UAB, we'd accomplished that mission. So we had actually identified treatments for several other ultra rare disease patients in less than 12 months, using that systematic process I outlined earlier. And then what happened is, I came to UAB. So I got the offer of a lifetime to come, become the director of this institute, and to build it up from scratch, and to realize this vision of precision medicine for all. So that is the mission of our institute. What we are trying to do is scale up everything I've just showed you for rare disease for everything else. So we are doing this for all rare diseases for sure. It will always be near and dear to my heart to help the rare disease community. But we're also very active and aggressive in going after cancer. So we want to be able to do precision medicine for all cancers as well, and ultimately for all diseases. My goal is that someday when we think about precision medicine is that we just think of it as medicine, because that's just what we do now. That's the hope. So I'll talk a little bit about what we're doing. And I have to say, because we get lots of patients now coming into the Institute asking for help, rare disease patients, cancer patients, Alzheimer's patients, depression patients, you name it, they're coming in, and we're trying to find ways to help them. And what we've done is we are actually executing that battle plan for rare disease, and I just have to give some credit to the team now, because I've actually got an amazing team that really does the bulk of the work when it comes to implementing this battle plan for precision medicine. And the amazing thing is that the three on top, those are what we call our precision medicine specialists. They actually put together the research plans for the patients and make sure these things are actually working, and they're all undergrads. So we've got some very bright undergrads here in Alabama and here at UAB. We're partnered with folks all over campus. So within the Institute and adjacent to the Institute, we have Dr. Bruce Korf, who runs, among other things, the Undiagnosed Diseases Program. So if you come to the Institute with an undiagnosed disease, and you've been on a diagnostic odyssey for several years, we're going to send you to Bruce. And Bruce has a big team in place where they can do the same kind of thing that we did for my son Bertrand, but at scale. So that people can come in and we can try to find, if necessary through the genome, the root cause of their disease. And then once you're done with Bruce, you'll come back to us and we will try to find a treatment for that disease. Well, of course, we've also got a battle plan for cancer. In fact, before I ever came here, I was meeting with Eddie Yang, who's here. He's now both the deputy director for the Precision Medicine Institute and the associate director for precision oncology. And the reason I liked Eddie the moment I met him is that he started showing me battle plans. He was developing his own algorithms for how to go after mutations in cancer. These have evolved considerably since. And just to give you a sense of what we're really doing at UAB now, because Eddie's running 2 clinical trials in this space, is what does it mean to do targeted cancer treatment? What does that even mean? Well, what it means is we're going to look inside the tumor genome. We're going to look at the mutations driving the cancer. So if we see the tumors lit up with several mutations all over, then what we can do now that we couldn't even do a decade ago is actually see them. So we actually know where to shoot. And so then there's going to be a process of matching those mutations to the treatments that might work for them. And in some cases, we actually can do that. I want to be clear that while we do certainly have some success stories, we do have a long way to go. Just because we can see the target doesn't mean we can always hit it. But we're getting better at this all the time. So I think just being able to see what we have to go after has been a monumental leap forward in cancer. And when we do hit it, the results can be quite remarkable. So I'll just share one story here, which is out in the public now, about one of the patients to go through Eddie's trials. He'd had prostate cancer for several years, and 42 rounds of radiation treatment, 17 rounds of chemotherapy, and it was just getting worse and worse and worse. And obviously, this is just miserable. And so when he comes in, we were able to sequence his tumors. We were able to identify the genetic mutations driving his cancer. And the strange thing here is that genetically speaking, his prostate cancer was closer to an ovarian cancer. I know it sounds strange because he's a guy, but this can happen. And so what that meant was he needed an ovarian cancer drug for his prostate cancer. And the crazy thing is, it worked. Well, it's not so crazy, it's just science. Because if you know the root cause and you have a way of targeting that root cause, that's what you do. So he had a really remarkable turnaround, in fact. And he had PSA levels that are the way you measure prostate cancer, very close to normal within, I think, just a few months. So then there's a question of, well, what if nothing works? Or what if it becomes resistant to everything you've tried? Well, at UAB and at the Institute and the Cancer Center, we're developing a defense-in-depth strategy. So one of the next things we're doing is what I would call the try-it-all approach. So just try every single drug that's out there, whether it's approved, whether it's in clinical trials, or if it's a nutritional supplement you can buy at GNC. We just want to try everything and see what you can do. So we are piloting this with leukemia. So for certain forms of leukemia, if you are treatment resistant, we can take your blood, we can take them over to Southern Research because we're partnered with them, and we can just try every single drug. This is around 2,000 drugs. And we will check to see if any of them has the effect of mitigating leukemia for your cells specifically. And I just want to give credit to Dr. Chris Klug, who's actually been the scientist driving this project. And what's remarkable is every time we've taken blood, we've always found something. We usually find several things, in fact, that will work. And what's perhaps not surprising is the top hits are never cancer drugs. These can be drugs that, honestly, literally the best that we've ever seen is a drug you would typically give to a dog for worms, and yet here we have an opportunity to use it for cancer. We've seen other drugs that are meant for cholesterol. I mean, we've seen all sorts of stuff pop up when we do these screens. So this is a game changer for cancer because it widens the arsenal we have to shoot at it to the entire FDA-approved library, and again, plus everything that's in clinical trials. That's a huge advantage because when you run out of drugs, you've got new options here. The other thing I'll mention is that we're actually, we're so pleased with how this is going that we want to deliver this to everybody. So we're going to try to spin this off as a company so that I would hope someday the blood from every leukemia patient in the country and even the world would come here to UAB, and we would actually find the treatment for them here. So what if that doesn't work? What if we tried everything and there was nothing? Well, that's where the third arrow and the strategy comes into play. And so I've talked to Mike Beer, the Cancer Center director, and it's clear that UAB is going to move into places in a space called immunotherapy, where there's a number of ways that you can get the immune system re-engaged in fighting the cancer again if the cancer's evaded it. And I want to also mention before I close out that there are ways that you can engage to lower your own personal risk through initiatives we have here in the state of Alabama that are run out of UAB, like the Alabama Genomic Health Initiative. So you can sign up, and if you do, we will screen you for 54 preventable genetic conditions, many of which are actually hereditary cancers. So if you have a family with a very high recurrence of cancer, I'd encourage you, it's a free program, to go sign up for this. And we can spot many of the hereditary cancer mutations through the tests that we do. We can't spot all of them. We can spot a large number of them. And so if we tell you that you have a hereditary cancer risk, what will come with that is some actionable recommendation too, perhaps around screening or maybe some other preventative things that you can do to minimize your risk of that cancer. There's actually a lot more we're doing at the Institute. Obviously, it's not all about cancer, so I'm not going to talk about that today. Just want to say that this is something that is encompassing, that precision medicine is a philosophy that we're applying really to everything, and cancer happens to be one of the best possible targets for this new way of doing medicine. So as far as the war on cancer goes, obviously we have a long way to go. But I think, and I hope you, from what I've said today, you understand that this is a war that we can win. We can win the war on cancer. Now, it's not going to be a short fight, but we can win it. So I think we will win it, and absolutely UAB will. So with that, I thank you, and I would be happy to take any questions you have.
How great that you're right here in our
It is great. I love the food here.
Dr. Mike, you had mentioned how for cancer, for like rare cancers and some certain advanced cancers, we could do genomic sequencing.
Mhm.
Are we at the point where we can do it for just every person?
Well, yes. I mean, there's no reason we couldn't do it for early stage cancers as well. But hopefully, if it's early stage and you catch it early and you just take it out, there's no need for this. I personally, I would do it for stage 1 because that's my approach, and I think someday, honestly, we will because the costs just keep falling and falling and falling for doing this. So someday it'll be very routine to do it. And for sequencing itself, I think at some point we're going to sequence everyone at birth. I mean, there are projects doing this right now. So you'll start life knowing a lot of what your risks are, and maybe even some ways to fight against that for your entire life.
You mentioned work with veterans.
Mm-hmm.
Are you doing any research that would be related to environmental causes for cancer, burn pits and such?
Absolutely. I'm glad you brought that up because one of the big programs I worked on through the White House was the Million Veterans Program. And what this is doing is it is literally enrolling 1 million veterans. I think they're up in the 600,000s now. They're collecting their whole service history, their whole health history, and they're also collecting their genetics. So you have this huge database that brings together the environmental factors, the genetic factors, and the outcomes to make very powerful predictions about what could be potentially driving the cause of not just cancers but many diseases. So for example, ALS occurs at about twice the rate among service members. So there's clearly some environmental factors there that are going on. In fact, ALS is a special sub-project within the Million Veterans Program. But yeah, we're absolutely, as a scientific community, looking at the environmental factors here, and in particular with veterans in particular, to see if there's anything that we can learn from them, and then anything we can do for them. Are y'all going to go sign up for AGHI? It's over in Kirkland Clinic. Do it today.
And it's free.
And it's free. That's right. It's free. Anybody can do it. Yeah.
How do you feel about like 23andMe and those sort of others? Do those cover some of the same stuff or not really?
Yes and no. So 23andMe knows an awful lot about you, but they don't tell you everything there is to know about you. So if you want to know more about yourself, download your raw data from 23andMe and then run that through a reinterpretation process. If you don't know how to do that, come talk to me, and we will show you how that's done. But yeah, you can reanalyze your own raw data, and you will learn an awful lot about yourself from that. Yeah. And actually, as far as cancer is concerned, I think 23andMe did get approval to warn about certain cancer variants now. And I think BRCA in particular. For certain mutations in BRCA, they can warn you if you're at risk for breast cancer. Yeah, but in general, I'd say I'm very much in favor of democratizing genomics. I'm thrilled to see companies like 23andMe and others that are in this space giving people access to their genetic data.
What about the ethics involved with pre-existing conditions, et cetera?
So, wait, you mean not yet pre-existing, but will be pre-existing conditions? Yeah. So let's talk about Alzheimer's for a second. When I got my own genome sequence for the second time, where I could actually get access to the data, the first thing I did was max out my life insurance, because if I had found out that I was predisposed, there was no way I was going to get it at that point. And so this is something that I tell folks, that you're not protected by law from discrimination in life insurance. There are protections around health insurance, but for life insurance, there are not. And this is a real issue for some people, where they have incidentally learned that they're at risk. And so this is why if you do 23andMe, they're going to make you ask, do you really want to know, before you check that box and find out. So there are definitely ethical concerns. We actually have an ethicist on faculty at the Institute for this exact reason. Because we would, as we're doing this, we're figuring out the ethics as we go, and so to have ethics professionals, guiding us in this, I think is an advantage, because there's all kinds of stuff that comes up with precision medicine, for cancer and beyond, and we want to make sure we do it right. And I think a key component of this is, with the predictive power of genetics, we want to make sure that we always do what the patients want us to do. So if a patient doesn't want to know, We want to know that, and we want to make sure that we don't tell them. And if they do want to know, we want to make sure that they really understand everything we're about to tell them and the risks that are involved in knowing what we can tell them. Yeah.
So if you join the AGHI, this may be more similar to this too, but if you join the AGHI and you do get that information, are you saying that your life insurance is at risk?
No.
That information, or your health insurance is at risk? 'Cause I think
So-
there are questions around that.
That's a good point. So with AGHI, if we contact you about a result like that, it's because there's something you can do. And so there's an action associated with it to mitigate the risk. So I would hope any reasonable life insurance company would realize that, oh, you've been informed, you know how to mitigate this risk now. They should see that as a benefit. As a matter of fact, I have talked to Protective Life in town about exactly that. Can you actually inform people of their risk so that they can take better care of themselves to actually mitigate it. So I think AGHI is, I won't speak for any particular insurer, but I think it's a strictly positive thing to do in that regard. Yeah.
Actually, I'm part of the AGHI study, and I submitted some concerns. I'm thinking also, I mean, like, I don't have any.
Well, that's good.
So I would like to go further, and because I think that the diseases that where they're obviously, I would have been sick by now if I.
Right.
Yeah. So
Yeah.
In my opinion, I don't know, it was quite superficial. Yeah. I would prefer to go further and deeper.
Absolutely.
Is there an opportunity like that?
Yes, so we are very actively pursuing other ways that we can responsibly return results within AGHI. So, for example, we're looking at returning ancestry data. We may even be looking at ways to return raw data if people want to do a reinterpretation on their own. We haven't made any concrete decisions about exactly how to return all this because, again, there are real ethical considerations that we have to take into account here. But I think the mood amongst the AGHI investigators is we want to find a way to let you engage with this data, and because it's your data. And so we're just figuring out how to do that in the most responsible possible way.
All right, if there are no more questions, we also have.
Thank you.